Okay, so we're going to actually continue on a previous lesson, but we're going to make it a little bit more complicated. So the impact of transforming data on statistics. So we've done transformations already, but now we're actually going to be going beyond just adding, multiplying, and dividing, and subtracting, of course, and look at combining different sets of data, which brings up my cartoon. Use the CRS database to size the market. That data is wrong. Then use the SIBS database. That data is also wrong. Can you average them? I could teach you how to average them. Sure, I can multiply them too. But again, bad data in, bad data out. So let's go ahead and look at some good data. We have a dice game where you can earn 0, 5, or 50 points depending on what you roll. And we calculated the probabilities of getting 1, 2, or 3 was a half, 4 or 5 is a third, and getting a 6 is 1 out of 6. So we're going to go ahead and determine the expected values. Now I could easily put this in my calculator and have it spit it out for me. But I want you to get into the habit of, especially if it's a short table like this, to go ahead and write out the expected value formula, which is your value times that probability, x times p of x, and add them all up, in which case we get 10. Now I'm going to go ahead and show variance, which is also on your formula chart. And yes, your calculator can spit it out, but this is not hard to write. So go ahead and write it. I will expect you to write these. And you get 325. Now your standard deviation for this is a square root, or about 18.03. So, okay, so there's our expected value and standard deviation. But let's put a twist on the game. We're going to triple the points. I don't know why we're feeling so generous, but we are. And I'm going to go ahead and calculate. So the only thing that changed here are these numbers. So my expected value, everything in here is tripled once, so my expected value triples, and that makes sense. When I do my variance, I get a much bigger number than I used to have. I had like 325, but when I square root it, I get 54.08, which is roughly my 18.03 tripled. So that's making sense so far, right? Okay, let's subtract 50 points from each value after tripling, and what happens to the mean and standard deviation? Well, now I have these values, and I'm going from the 150 point game, and I have minus 20, and I find my variance. Hey, that's the same number. Interesting. And my standard deviation is unchanged. Well, my expected value decreases by 50 points because my distribution shifts down by 50 points, but the spread, the standard deviation, remains unchanged because from my smallest to my largest, this spread is still 150 points apart. So there's no real change in the standard deviation. Oops. So let's look at playing the game, same game twice in a row. So you're going to say, hey, we'll just double the mean and double the standard deviation. Well, this is where it gets a little tricky, and it's very easy to make a mistake and think that you're in a situation where you can just double things. And let me explain why. We're going to do a tree diagram of all the probabilities for these outcomes. If your table has a 60, put a line through it. All right, so these are all the possible outcomes. How did I figure that out? Well, I did my lovely tree diagram. On my first roll, I can get 0, 5, or 50 points. If I roll a 0, what's possible in the next roll? Oh, it's still 0, 5, or 50, and so forth. So now I'm going to go through all the trouble of multiplying these out. Yes, I did. If I can do it, you can do it. Mine are typed up. All right, so these are all the probabilities for all these outcomes. Now, I felt a little awkward writing probability of, say, 5, because that's a probability of 5 on this branch. There's another probability of 5 here. So probability of getting 0, 2 zeros in a row is 0.25. There are 2 5s, so that means I have to combine these two, and that gives me 0.33. For 10, there's only one of those. For 50, there's 2 of them, so combine those two, and I get 0.167. 55 also has 2, so that's 0.111, roughly. And 100 has just 1, which is 0.028. And when you add these all up, they should be very close to 1. There might be some rounding errors, but that's okay. These actually do add up to 1. All right, so what happens with our data? Well, I'm going to use technology, put these numbers in my calculator. Could I write out the formula? Absolutely. So I could say 0 times this plus 5 times this, etc. All right, but that's not the point I'm trying to get into right now. So I have my expected value is 20. My standard deviation for y is 25.5, and my variance is 650. Well, let me compare them to when I played the game just once. My expected value was 10. My standard deviation was 18, and my variance was 325. Well, okay, expected value is very lovely because it behaves as you expect it to. The expected value for y, playing it twice, was just twice the expected value for playing it once. But the variance for playing it twice was twice the value for playing it once. But because standard deviation is the square root of variance, it doesn't behave exactly the same. All right, so let's go ahead and look at that. So the standard deviation of y is not double the standard deviation of x. Why is that? Because we're playing the game twice. So summarizing, when we have more than one outcome being combined, I don't mean just taking the result and multiplying, but you're taking an outcome and another outcome. So rolling die twice, combining different things, or even combining two attempts at the same thing. We can't just add standard deviations, but we can add variances. So here are the rules for combining expected values and variances of combined variables. Expected value, super easy. Treat it like you think it should behave. If you're adding two outcomes, add the two means. If you're subtracting two outcomes, subtract the two means. Yay, that's easy. Variances are almost as well behaved, but they have an add because this is sort of related to the Pythagorean theorem. So let me show you standard deviation. This is a standard deviation, but it looks more like this. And if we go back to when we derived the standard deviation, remember how we were squaring and adding and then taking the square root eventually? Same idea. It's like the Pythagorean theorem of standard deviation. So you'll never see a minus in there. When you combine two outcomes, you're actually increasing the spread. You're never making the spread smaller. So if we were subtracting two outcomes, that doesn't mean. Okay, so we have an example. A used car dealer runs autos through a two-stage process to get them ready to sell. The mechanical checkup costs $50 per hour and takes an average of 90 minutes with a standard deviation of 15 minutes. The appearance prep, wash, polish, etc., costs $6 per hour and takes an average of 60 minutes. Notice I have minutes and hours, so be careful. And I have a standard deviation of 5 minutes, all right? So what are the mean and standard deviation of the total time spent in the car? So I can go ahead and just look at minutes right here. We think that two phases are independent, so variances add. So I have my mechanical time as m, a is my appearance time, and t is my total time. So my expected value for total is my expected value for mechanical plus expected value for appearance, which is just adding them, and you get 150. Easy peasy. Now my variance for t is going to be adding those two variances as well. So I'm going to do 15 squared because variance is standard deviation squared plus 5 squared. I get 250. And when I square root that to go back to standard deviation, I get 15.8 minutes. So we expect the total prep time to take an average of 150 minutes with a standard deviation of 15.8 minutes. Now, what is the mean of the total expense to prepare a car? So in this one, we're going to go ahead. We have some multipliers, right? So my expected value for hours is 1.5 hours. My cost is $50 per hour, right? So my expected value should be pretty easy. So I'm going to do 50 times the hours. Now make sure you do hours. And 6 times the hours for appearance. And I can just do this, right? So I get $81 as the expected expense, all right? What is the standard deviation of the total expense? So let's go ahead. We're going to set up, a multiplier does affect spread, so we have to incorporate this cost per hour. So my standard deviation for mechanical hours was 0.25. The cost is $50 an hour. My standard deviation for appearance is 0.1 hours. So notice I'm changing to hours here. It's $6 per hour. So my variance for the total cost, I have to do, remember I'm doing variance. So I'm going to take this 50 squared. Why am I doing 50 squared? Well, because if I do the variance is the square of standard deviation, right? And so this would just normally, if I just did this on the standard deviation for this is just 50 times that. But I'm doing variance, so it squares it. So I have 50 squared times variance of m. Notice this is variance, not standard deviation. All right? So I'm going to get basically this, 2,500 times 0.25 squared plus 36 times 0.10 squared. Ugly number, 156.5. Could be worse. So take the square root of that, and I take my standard deviation. So again, if you wanted to do this without paying attention to the variance, all you have to do is make sure you square that multiplier. Or you could say your new standard deviation just for this is $50 times 0.25, which would be like $12.50, right? And then you're going to take that and square it. And then you could say, okay, this is $6 times 0.1, so you get 0.6, and you take that and square it. So there are two ways to do this. You can actually look at the variances, remembering that these are squared, or you could calculate your new standard deviations, then square them to get my new variance, and then square root that, kind of like the Pythagorean theorem. So there are two ways to kind of tackle this. Use the one that you feel most comfortable with. All right, what is the mean of the differences in cost in the two phases of the operation? So again, we got our expected value in hours is $1.5 hours, and the cost is 50. And my expected value for appearance is 1 hour with a cost of 6. So I'm going to go ahead and say, because I'm doing the expected difference in cost, I have to do the cost, find the expected values for the cost, and subtract those. So this one's pretty easy, right? Expected values are always pretty easy. Now let's go ahead and find the standard deviation. Well, this is the interesting part. Because we always add there. Ooh, I think I have a typo on your notes. Make sure that's a plus. Well, yeah, make sure that's a plus. I think on the slide before I said plus minus. That's plus. Always plus. All right. So we have 50 squared plus, and again, I'm working in variances. I'm squaring this because I have to, the multiplier here goes on the standard deviation, so that's squared and that's squared. All right, so they're both squared. And then I take the square root. So my standard deviation is 1251 once I do all that. So what is the probability that it will take longer to do the appearance prep than the mechanical checkup? All right. So we need to assume a normal model to make any calculations. This means the differences in time will vary normally as well. All right. Well, we have our difference in time. Our average is 30 minutes, our expected value. Easy peasy. Our standard deviation is 15.8 minutes. Well, what I'm going to do is, if the appearance takes longer, is this value going to be positive or negative? Let's see. Probably take longer to do the appearance prep than the mechanical checkup. Well, that means that this would be negative, right? So we expect the average difference in prop times to vary according to this normal model, with an average of 30 and a standard deviation of 15.8. So we're kind of jumping here to the gun. Here is where that 0 comes in. So if appearance takes longer, that means we're looking at 0 and before. So we find the z-score, negative 1.899, and we find this value for our normal CDF or our table, and voila, 2.88% is the probability.